The universe you see is a grand illusion shaped by forces hidden from our senses. Galaxies spin too fast, held together by an invisible scaffold. The cosmos expands at an ever-increasing rate, pushed by a mysterious pressure we call dark energy. These are just two of the unseen architects building the reality we perceive. We are about to journey through 30 of these cosmic forces, from the quantum foam that birthed all structure to the fields that give particles mass. By the end, you will understand the fundamental, invisible machinery that orchestrates everything from the atom to the galaxy. How did the faintest quantum whisper grow into the cosmic roar of galaxies? And what does the emptiness of space itself hide? What single force do you believe most profoundly shapes our existence? Our reality is built upon a ghost. The very first of our unseen architects is dark matter, a substance that does not emit, absorb, or reflect any light, making it completely invisible to our telescopes. Yet we know it is there because of the immense gravitational pull it exerts on everything we can see. The story of its discovery begins not in the vast emptiness between galaxies, but within them. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies. She found something that defied the laws of gravity as we knew them. Stars at the outer edges of these galaxies were moving just as fast as those near the center. According to Newtonian physics, those distant stars should have been flung off into the void, like a child spun too fast on a merry-go-round. The only explanation was that the galaxies were embedded within enormous, massive halos of something unseen, a dark gravitational glue holding everything together. This revelation sparked a cosmic treasure hunt that continues to this day. Deep beneath mountains, in abandoned mines shielded from the constant rain of cosmic rays, scientists have built exquisitely sensitive detectors. These laboratories wait in profound silence, hoping for the once-in-a-lifetime event, a tiny ping from a dark matter particle bumping into an atom of ordinary matter. So far, the particles themselves remain elusive, ghostly phantoms slipping through our finest nets, yet their influence is everywhere. Dark matter is the invisible skeleton of our cosmos. It formed the first gravitational wells that ordinary matter could fall into, seeding the birth of galaxies and sculpting the vast, web-like structure of the universe. Without this dark scaffolding, galaxies would have never coalesced, stars would not have ignited, and we would not be here to ponder the mystery. It is the silent, dominant partner in a cosmic dance, governing the fate of everything we see from the shadows. But if dark matter is the gravitational glue holding the cosmos together, its cosmic counterpart is a force of cosmic repulsion. Dark energy is the name we give to this mysterious phenomenon, a pressure inherent to the fabric of space itself that is causing the expansion of our universe to accelerate. Its discovery in the late 1990s was a profound shock, completely overturning our expectations for the ultimate fate of all things. Astronomers were observing distant stellar explosions, called Type 1, a supernova, to measure how fast the universe was expanding. They expected to find that the gravitational pull of all the matter in the cosmos was slowing the expansion down, like a ball thrown upward, gradually losing speed to Earth's gravity. Instead, they saw the opposite. The most distant supernova were dimmer than they should have been, meaning they were farther away than anyone had predicted. The expansion of the universe was not slowing, it was speeding up. Something was actively pushing the galaxies apart. This something is dark energy. Think of the universe not as a collection of galaxies, but as the surface of a balloon being inflated. Dark matter are the dots drawn on that balloon, clumping together. Dark energy, however, is the force that stretches the rubber itself. It is a property of empty space, a kind of negative pressure that grows stronger as the universe expands and creates more space. With every passing moment, the influence of dark energy increases, stretching the cosmic canvas on which everything is painted. This leads to a chilling and lonely future. If dark energy continues to dominate, as all evidence suggests it will, the fate of the universe is not a fiery collapse, but an eternal, cold drift. Galaxies beyond our own local group will eventually be pushed away so fast that their light can never reach us. The cosmos will become a vast, ever-darkening expanse, with islands of galaxies isolated from one another for all time. This force, born from the vacuum of space itself, is actively writing the final chapter of reality. The dominant forces of dark matter and dark energy sculpt our universe on the grandest scales, but the story of all structure begins with something far stranger, in a realm where the very idea of nothing loses all meaning. At the subatomic level, empty space is not empty at all. It is a turbulent sea, a quantum foam where particles and antiparticles spontaneously flicker into existence and then annihilate each other almost instantly. This ceaseless, chaotic dance is a direct consequence of the uncertainty principle, a fundamental rule of quantum mechanics that tells us we can never know both the exact energy and the exact time of a system. For a fleeting moment, energy can be borrowed from the universe to create a particle pair, a debt that is repaid the instant they vanish. It seems like a ghostly, microscopic phenomenon with no possible consequence for our world. But these quantum fluctuations are the primordial seeds from which every galaxy, star, and planet ultimately grew. The connection between this subatomic chaos and the cosmic structures we see today is one of the most profound in all of science. In the first fraction of a second after the Big Bang, the entire observable universe was compressed into a space smaller than an atom. At that scale, quantum fluctuations were not microscopic. They were the only structures that existed as the universe underwent a period of hyper-fast expansion known as inflation. These tiny, random wrinkles in the fabric of reality were stretched to enormous sizes. Regions that were slightly denser due to a quantum fluctuation became the gravitational wells that dark matter and then ordinary matter would eventually fall into. The universe was imprinted with a faint blueprint of its own future. We can still see this blueprint today, etched into the oldest light in the cosmos. The cosmic microwave background is a snapshot of the universe when it was just 380,000 years old, a time when it cooled enough for light to first travel freely. This afterglow of the Big Bang is not perfectly uniform. It contains tiny variations in temperature, mere millionths of a degree. These hot and cold spots are the direct, amplified imprint of those initial quantum fluctuations. The slightly denser patches appear cooler, the less dense ones warmer. Every galaxy supercluster we see today, every vast filament of the cosmic web, corresponds directly to one of those tiny specks in the ancient sky. The grand tapestry of our universe, with its billions of galaxies, was woven from the faintest whispers of the quantum void. These quantum whispers gave our universe its structure, but for that structure to become solid, for matter to truly become matter, something else was required. An invisible field of energy had to awaken and fill the cosmos, transforming a formless soup of particles into the tangible stuff of reality. This is the Higgs field, a fundamental presence that permeates every cubic inch of space, from the void between galaxies to the air in your lungs. Its purpose is deceptively simple. It gives particles their mass. Without it, every fundamental particle would zip through the universe at the speed of light, unable to form atoms, molecules, or us. The best way to understand this is not through complex equations, but through a simple human scene. Picture a crowded room where a popular celebrity is trying to walk from one side to the other. As they move, they are constantly surrounded by admirers, shaking hands and signing autographs. This interaction dramatically slows their progress, giving them a kind of social inertia. This is analogous to how some particles, like the top quark, acquire a large mass. They interact strongly with the Higgs field, which acts like that crowd, clinging to them and slowing them down. Now imagine an unknown person walking through that same room. They slip through the crowd with ease, barely interacting with anyone. This is like a particle with very little mass, such as an electron. It feels the Higgs field only weakly, and then there is the photon, the particle of light. It is like a ghost moving through the crowd entirely unnoticed. It does not interact with the Higgs field at all, which is why it travels at the ultimate speed limit, the speed of light. The discovery of the Higgs boson particle at the Large Hadron Collider was a monumental achievement, but it is crucial to understand what that discovery really meant. The boson is not the source of mass itself, it is merely a ripple, a tiny excitation in the omnipresent Higgs field, like a splash in an infinite ocean. Finding that splash was our proof that the ocean itself is real. This field is the true architect of materiality, the silent, constant presence that makes our solid, stable world possible. It is the reason anything has substance, the reason you do not simply dissolve into a blur of light-speed energy. The Higgs field is the unseen ground upon which the entire edifice of our material reality is built. While the Higgs field gives substance to the particles of our world, another quantum phenomenon weaves them together in a far deeper way. Two particles can become so intimately linked that they share a single existence, no matter how far apart they are pulled. This is quantum entanglement, a connection Albert Einstein himself famously dismissed as spooky action at a distance. The spookiness begins with a concept called superposition. Before a particle is measured, it does not have a single defined property like spin or polarization. Instead, it exists in a blur of all possible states at once, a ghostly combination of possibilities. Now imagine you create two particles that are born together, instantly becoming entangled. They are like a pair of magical coins, each spinning continuously. The moment you stop one coin and see it land on heads, you know with absolute certainty that its partner, even if it is now on the other side of the galaxy, has instantly landed on tails. This is not a signal traveling between them. The information is not transmitted. The connection is instantaneous, a fundamental reflection that the two particles are not truly separate entities, but part of a single, unified quantum system. This challenges our most basic intuition about space and locality, suggesting that the universe is fundamentally interconnected in ways we are only beginning to fathom. This profound interconnectedness is not just a philosophical curiosity, it is the bedrock for emerging technologies that sound like science fiction. Quantum computers use entangled particles, called qubits, to perform calculations. Where a classical computer bit can only be a 0 or a 1, a qubit can be both at the same time, allowing quantum machines to explore countless possibilities simultaneously. This could allow us to design new medicines by simulating complex molecules or solve logistical problems that would take today's supercomputers billions of years. Entanglement also enables quantum cryptography, creating theoretically unbreakable codes. Any attempt to eavesdrop on a message secured by entangled particles would immediately disturb their delicate connection, alerting the sender and receiver to the intrusion. The same spooky linkage that baffled Einstein could one day form the backbone of a perfectly secure global communication network. It reveals a cosmos where separation may be the true illusion, and every part of the universe is subtly, instantly, and mysteriously tied to every other. This cosmic interconnectedness emerges from a foundational event of unbelievable violence. To understand the universe we see, we must travel back to the very first moments of its existence, to a force of unimaginable power called cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe underwent a growth spurt so extreme it defies all analogy. It expanded faster than the speed of light, doubling in size over and over again until a region smaller than a subatomic particle was stretched to a scale larger than our entire observable universe. This was not an explosion of matter into space, but a sudden, explosive stretching of space itself. The driving force behind this event is thought to be a unique, high-energy state of a quantum field, a cosmic cousin to the Higgs field, which generated a powerful repulsive gravity. This single, brief period of hyperexpansion solved several profound mysteries about our cosmos. First, it explains why the universe is so remarkably uniform. Look in any direction, and the distant cosmos looks essentially the same, with the same density and temperature. Without inflation, these regions would never have had time to communicate and even themselves out. It is as if you took a tiny, crumpled ball of clay and stretched it into a vast, perfectly smooth sheet. Inflation was the stretching that ironed out all the primordial wrinkles, creating the flat, uniform canvas we observe today. Yet it did not erase all structure perfectly. Incredibly, it was the microscopic quantum fluctuations in that inflationary field, the very same quantum jitter from the void, that were stretched to cosmic proportions. These tiny, random differences in energy became the slight variations in density that gravity would later amplify into galaxies and galaxy clusters. The same force that made the universe smooth also, paradoxically, gave it the seeds of all its future complexity. The search for direct evidence of inflation is one of modern cosmology's great quests. The theory predicts that such a violent stretching of spacetime would have generated powerful ripples known as primordial gravitational waves. These waves would have left a faint, twisted pattern in the polarization of the cosmic microwave background, a unique signature often called the smoking gun for inflation. While we have strong indirect evidence, this definitive signal remains elusive, hidden in the faintest whispers of the universe's first light. Cosmic inflation set the stage for everything. It established the initial conditions of smoothness and flatness, and it provided the primordial blueprint from which dark matter and dark energy would later sculpt the cosmic web. Without that fleeting, explosive moment, our universe might have remained a small, chaotic, and lifeless knot. This same cosmic violence that forged the universe's structure also forged the very atoms that make you. Deep within the heart of every atom, a battle of unimaginable ferocity is taking place, a silent war that holds your very existence in the balance. The strong nuclear force is the ultimate victor in this conflict. It is the most powerful fundamental force in nature, yet it operates on such a tiny scale that its influence ends at the border of the atomic nucleus. Its primary role is twofold, and both are absolutely essential for our reality. First, it binds quarks together to form the protons and neutrons that are the building blocks of atomic nuclei. Second, and just as critically, it uses those protons and neutrons as its building blocks to bind the nucleus itself together. Think of the nucleus of an atom like the nucleus of a helium atom. It contains two protons, each with a positive electric charge. As you might remember, like charges repel each other, and the closer they get, the stronger that repulsion becomes. Inside a nucleus, these protons are squeezed so close together that the electromagnetic force trying to blast them apart is astronomical. It is like trying to press the north poles of two powerful magnets together with all your might. They desperately want to fly apart. The strong nuclear force is what overcomes this tremendous repulsion. It acts as an incredibly powerful, short-range glue, locking the protons and neutrons into a stable cluster. Without this force, every atomic nucleus in the universe would instantly explode, and atoms, as we know them, could never form. The carrier of this mighty force is a particle called the gluon. The name is perfect, as these particles are the ultimate subatomic adhesive. They constantly jump between quarks, creating a powerful bond that holds them in perpetual confinement. This bond is so strong that no quark has ever been observed in isolation. If you try to pull two quarks apart, the energy you put into separating them is used to create new quarks, much like stretching a rubber band until it snaps, only to find you are now holding two smaller, intact rubber bands. This phenomenon, called color confinement, ensures that quarks are forever imprisoned within particles like protons and neutrons, making stable matter possible. The consequence of this force's victory over electromagnetism is everything you see and are. Because atomic nuclei can be stable, electrons can orbit them, forming a vast and stable periodic table of elements. This stability allows for the complex chemistry of carbon, oxygen, and iron, the very chemistry that forms planets, oceans, and life. The strong nuclear force is the quiet, unyielding guardian of the atomic realm, the reason the universe is filled with solid, lasting things instead of a fleeting, formless cloud of fundamental particles. While the strong force builds stable atomic hearts, another, more subtle power works to dismantle them. The weak nuclear force is the agent of change in the subatomic world, the quiet architect of transformation that makes the sun shine and the very ground beneath your feet slightly radioactive. Its power lies not in binding things together, but in altering the identity of particles themselves. This force is responsible for a process fundamental to the universe, radioactive decay. In a heavy, unstable nucleus, the weak force allows a neutron to transform into a proton, ejecting an electron and an almost massless particle called a neutrino in the process. This act of alchemy changes the very element, moving it down the periodic table toward stability. Without this slow, steady decay, the internal heat that keeps the Earth's core molten would have faded away billions of years ago, leaving our planet a frozen, geologically dead world. The messengers of this transformative force are the W and Z bosons. These are incredibly massive particles, far heavier than an entire iron atom, which makes the weak force profoundly short-ranged. It operates only across the width of a single proton. The immense mass of its carrier particles is also why the weak force is, as its name implies, so weak compared to the mighty nuclear glue. But its subtle influence reaches far beyond a single atom. This same particle changing process is the first, critical step in the nuclear fusion that powers the stars. In the core of our Sun, the intense pressure and heat force protons to fuse. The weak force is essential here, allowing two protons to overcome their mutual repulsion by transforming one into a neutron, forging the first heavy hydrogen and releasing the energy that floods our solar system with light and heat. Every ray of sunshine that warms your skin is a direct product of this unseen, transformative power. Its most profound role, however, was played in the universe's first second. In the searing heat of the Big Bang, particles and antiparticles were being created and annihilated in equal measure. For our universe to exist, a tiny asymmetry, a 1 in a billion imbalance, had to favor matter over antimatter. The weak force is unique among the fundamental forces in not treating matter and antimatter as perfect mirror images. Through a process known as charge parity violation, it interacts with them slightly differently. This subtle bias operating in the frenzied first moments allowed a tiny surplus of matter to survive the great annihilation. Every galaxy, star, and planet, and every one of us, is made from that 1 in a billion remnant. The weak force, the quiet transformer, is the reason there is something rather than nothing at all. The same weak force that forged our material surplus now yields to a far more familiar, yet equally unseen, power. Electromagnetism is the artist of the visible world. the force that paints the rainbow, binds atoms into molecules and orchestrates the very dance of life itself. We see its effects in every flash of lightning and every shimmer of a soap bubble, but the force itself remains hidden, mediated by ghostly messengers called virtual photons. These are not the photons of light we see. They are transient particles, constantly flickering in and out of existence, borrowing energy from the quantum vacuum to create an endless exchange between charged particles. When two electrons repel each other, they are not pushing one another away like magnets on a table. Instead, they are furiously trading a storm of these virtual photons. It is this ceaseless, invisible exchange that we feel as the electromagnetic force, a push or a pull generated by the quantum chatter of the void. This force is the master architect of chemistry. It is the glue that holds electrons in their orbits around the nucleus, creating the stable shells that define how atoms interact. The specific strength of this electromagnetic glue is not arbitrary. It is defined by a number, the fine structure constant, which governs how strongly charged particles couple to the photon field. If this number were even slightly different, the entire edifice of our reality would crumble. Make it a little stronger, and electrons would be locked so tightly to their atomic nuclei that chemical bonds could never form. Atoms would remain isolated, forever unable to create the molecules of water or DNA. Make it a little weaker, and electrons would not be bound at all. Atoms would instantly fly apart, and no stable matter could exist. The force is exquisitely balanced on a razor's edge, powerful enough to build complex structures, but not so powerful as to freeze all change. This perfect tuning extends to the scale of life. Every nerve signal that fires in your brain is an electromagnetic pulse racing along a neuron. Every beat of your heart is triggered by carefully orchestrated waves of charged particles. The very shape of a protein, which determines its function in your body, is a direct consequence of the electromagnetic forces between its constituent atoms. From the vibrant green of a leaf capturing sunlight to the electric thrill of a thought, all of it is the work of this single, unifying force. Electromagnetism weaves the invisible connections that turn a chaotic soup of particles into a universe of light, form, and life. Electromagnetism weaves the world of light and life, but it bows to a far grander architect. Gravity reigns over the cosmos, yet its true nature is nothing like a simple pull. Einstein revealed that gravity is not a force in the traditional sense, but the very shape of reality itself. Mass and energy do not attract each other across a distance. Instead, they tell spacetime how to curve, and spacetime tells them how to move. The classic analogy is a stretched rubber sheet. Place a heavy bowling ball in its center, and it creates a deep well. Now roll a marble across the sheet. It does not travel in a straight line. Instead, it curves inward, tracing an orbit around the central mass. The marble is not being pulled, it is simply following the shortest possible path through the curved geometry. This is what a planet does. It is not being actively pulled by the sun, it is cruising along an invisible groove in the cosmic fabric, a path dictated by the sun's immense weight. This curvature explains one of gravity's most astonishing effects, the bending of light itself. Light has no mass, so according to Newton, gravity should not affect it. But if gravity is curvature, then light, traveling through that warped space, must also bend its path. We have witnessed this during solar eclipses, where stars positioned near the sun's edge appear slightly out of place, their light warped by the sun's gravitational well on its journey to us. Even our own planet creates a tiny dimple in spacetime, a curvature so slight we cannot perceive it directly. You do not feel gravity, you are responding to it. When you stand on the ground, the Earth's mass has curved the space and time around you. You are not being pulled down, You are being prevented from following the straight line you would naturally follow through the universe. The ground is constantly pushing up against you, and that is the force you feel. Your entire life is spent navigating the invisible, intricate contours of curved spacetime, a silent geometry written by mass and energy that guides the dance of planets and the fall of a single leaf. This silent, curved geometry of gravity, however, confronts its most baffling contradiction in the nature of empty space. The quantum vacuum, that seething sea of virtual particles, should be a source of immense energy. Every cubic centimeter of nothingness, according to our best quantum theories, should be boiling with a power so colossal it would have torn the universe apart in its first instant. The staggering mismatch between this prediction and our calm, slowly expanding reality is the greatest unsolved problem in fundamental physics, known as the cosmological constant problem. We can calculate the energy that these quantum fluctuations should contribute to the vacuum of space. The number we get is absurdly, unimaginably large. It should curve spacetime so violently that the universe would either collapse or expand so fast that no galaxies could ever form. The reality we observe, however, is different by a factor of 1 followed by 120 zeros. It is the worst theoretical prediction in the entire history of science. Trying to grasp this discrepancy is like calculating that the air in your room should weigh as much as 1 billion galaxies, while your instruments measure only a few grams. Something is profoundly wrong with our understanding. The leading candidate to resolve this catastrophic mismatch is that the frenetic activity of the quantum vacuum might be the very source of the dark energy now accelerating the cosmos. In this view, the vacuum energy is real, but its effect is not the titanic force we calculate. Instead, it manifests as a faint, persistent pressure, a cosmological constant woven into the fabric of spacetime itself. This would mean that the same quantum jitter responsible for seeding the galaxies is also, in its mature form, pushing them apart. The energy of the void is writing 2 chapters of cosmic history, one of creation and one of eventual isolation. How can the same force be responsible for both the microscopic seeds of structure and the macroscopic fate of emptiness? The answer remains hidden, a ghost in the equations, reminding us that our understanding of nothing at all is the key to understanding everything. The profound quiet of the cosmic void might be broken by particles that do not just flirt with the speed of light, but live beyond it. These are tachyons, hypothetical entities born from a class of theoretical fields that rewrite the rules of reality. In our normal world, adding energy to an object makes it move faster, approaching but never reaching the universal speed limit. A tachyonic field turns this logic on its head. Its particles, if they exist, are born faster than light, and to slow them down toward the light barrier would require an infinite amount of energy. They are not speeding up, they are perpetual residents of a superluminal realm we can never directly visit. While no tachyon has ever been detected, the mathematics of their fields provide a startlingly elegant mechanism for one of the universe's most critical events. In the first searing moments after the Big Bang, the fundamental forces were likely unified, a single, perfect symmetry. For our complex universe to emerge, that symmetry had to break, much like a perfectly round pencil balanced on its tip must eventually fall to point in one specific direction. This is where a tachyonic field offers a compelling, though speculative, solution. Physicists theorize that such a field could have been in a high-energy, symmetrical state in the early universe. But this state would have been unstable, like a marble perched at the very top of a steep hill. A tiny quantum fluctuation would have caused the field to roll down into a stable valley, a state of lower energy. This descent, this spontaneous act of choosing one direction over all others, is what we call spontaneous symmetry breaking. The moment the field settled into its new state, the underlying rules of the cosmos changed. The single, unified force fractured into the distinct forces we recognize today: the strong, the weak, and the electromagnetic. The properties of this new vacuum state determine the masses of particles and the strengths of the forces, effectively locking in the laws of physics for the rest of cosmic history. The universe went from a state of perfect, featureless potential to one with specific rules and structures, all because an unseen field chose a direction to fall. The very fact that we have different forces, that particles have mass, and that chemistry is possible could be the frozen echo of a tectonic field's decisive transition, a ghostly signature from the first instant of time, forever imprinted on the fabric of reality. This cosmic geometry of curved spacetime, so beautifully described by Einstein, presents a profound puzzle when we descend to the quantum world. A complete theory of reality must reconcile the smooth fabric of gravity with the jittery, probabilistic nature of the quantum realm. To do this, physicists propose the existence of a ghostly messenger particle for gravity itself, the graviton. In the quantum model, every force is transmitted by a carrier particle. Electromagnetism has the photon, the strong force has gluons, and the weak force has the W and Z bosons. The graviton is the hypothetical quantum of gravity, a ripple in the fabric of spacetime so minuscule it has never been directly observed. It is believed to be a massless particle, like the photon, but with a crucial difference: it carries spin too, which corresponds to the tensor nature of gravitational waves. This theoretical particle would mediate the gravitational attraction between all objects with mass, not as a mysterious pull, but as an exchange of these invisible messengers, just as virtual photons mediate the electromagnetic force. The primary reason we have not found the graviton is gravity's incredible weakness. To understand this weakness, consider a simple magnet. A small refrigerator magnet can generate enough electromagnetic force to overcome the gravitational pull of the entire Earth, holding a note against the door. Gravity is so feeble that it requires planetary scales to become noticeable. Detecting a single graviton is, by extension, a task of almost unimaginable difficulty. A graviton interacts so weakly with matter that a detector massive enough to have a reasonable chance of catching one would likely collapse under its own gravity into a black hole. It is the ultimate cosmic hide and seek, yet the pursuit of the graviton is not a futile one. Confirming its existence would be one of the most monumental achievements in human history, the final, crucial piece needed to forge a theory of everything. Such a theory would seamlessly weave together Einstein's general relativity, which governs the cosmos, with quantum mechanics, which rules the subatomic world. It would provide a single, elegant framework to describe every interaction in the universe, from the birth of a black hole to the spin of an electron. The graviton is the missing link, the key that could unlock a unified understanding of all cosmic forces, revealing the hidden, singular melody beneath the apparent symphony of reality. The hunt for the graviton leads us to a different kind of ghost, a particle so elusive it could solve two of physics' greatest puzzles with a single, elegant answer. Actions are hypothetical particles, predicted not from the void of space, but from a profound symmetry within the heart of the atom. The mystery they solve is called the strong CP problem, a deep question about the strong nuclear force that holds atomic nuclei together. The puzzle is this: our most precise experiments show that the strong force seems to perfectly respect a certain symmetry between particles and their mirror images, and between matter and antimatter. This is strange because there is no fundamental reason in our theories for this to be the case. The equations naturally allow for a violation of this symmetry, which would make the neutron possess a tiny electric dipole moment, a sort of internal charge separation. If this existed, it would have profound effects, yet after decades of searching, we have found no such thing. the neutron is perfectly round to an astonishing degree of precision. The strong force is inexplicably perfectly balanced. Actions are the elegant solution. They are predicted to exist as a kind of cosmic correction, a field that dynamically adjusts to cancel out any possible symmetry violation, forcing the neutron to remain perfectly round. It is as if the universe has a built-in thermostat, constantly fine-tuning the nuclear world to maintain its perfect balance. This alone would make actions a monumental discovery, but their story becomes even more compelling when we look out at the cosmos. These particles are light, chargeless, and would have been produced in vast numbers in the hot Big Bang. Crucially, they would not interact strongly with ordinary matter, drifting through the universe like an immense, invisible fog. This makes them a perfect candidate for the dark matter that binds the galaxies. One cosmic ingredient could therefore solve two entirely separate enigmas: the puzzling symmetry of the strong force and the identity of the universe's missing mass. The quest to find them is as ingenious as the theory itself, since actions are expected to interact very weakly with matter, but may interact with strong electromagnetic fields. Scientists have built exotic detectors. These are not underground vats waiting for a collision. They are powerful magnets, often supercooled to near absolute zero, placed inside radio frequency cavities. The idea is that in the presence of a tremendously strong magnetic field, an action from the galactic dark matter halo might occasionally convert into a faint microwave photon. The experiment is essentially a high-tech radio receiver tuned to listen for the faint whisper of a particle transforming in the dark. It is a search for a needle in a cosmic haystack, requiring unprecedented sensitivity to hear the quietest of signals over the constant hum of the universe. Finding the action would be a breathtaking unification of the immensely large and the infinitesimally small, revealing a single, unseen actor playing two fundamental roles in the cosmic drama. The same cosmic phase transitions that broke the symmetries of the early universe may have left behind scars in the fabric of spacetime itself. Cosmic strings are theoretical relics from that violent epoch, one-dimensional defects of unimaginable density. Picture a crack forming in ice as it freezes, a line of imperfection marking a boundary between different regions. On a cosmic scale, this is what a cosmic string might be: a flaw frozen into the expanding universe as it cooled and its fundamental forces separated. These are not strings made of any ordinary material. They are pure energy, threads of spacetime curvature so dense that a single inch of such a string could weigh more than a mountain range. Their gravitational influence would be immense, warping the space around them. A cosmic string drifting through the cosmos would not pull objects toward it like a planet. Instead, it would slice through space, creating a unique kind of gravitational distortion. Light from a galaxy directly behind a string would be bent around it, not into a single smeared image, but into two identical, perfectly mirrored images of the same galaxy. This would be a telltale sign, a cosmic double vision that no other gravitational lens could produce so perfectly. The search for these phantom filaments continues in the oldest light we can see. As a cosmic string moves, it would create ripples in space-time, subtle gravitational waves that could leave a faint, linear scar in the patterns of the cosmic microwave background. Finding such a signature would be like discovering the fossilized crack in the frozen pond of our infant universe. These strings would be the ultimate cosmic fossils, relics from the first moments of creation, and their discovery would provide a direct, tangible link to the universe's most violent and formative transitions. Our universe is missing a fundamental piece. Every magnet you have ever held, from a simple refrigerator magnet to the entire planet Earth, comes with an inseparable pair, a North Pole and a South Pole. Break a bar magnet in half, and you do not get isolated poles, You simply create two smaller magnets, each with its own north and south, yet our deepest theories of physics suggest this should not be the final word. They predict the existence of magnetic monopoles, solitary north or south poles that wander the cosmos on their own. These would be particles of pure magnetism, massive and stable relics from when the electromagnetic and weak nuclear forces were a single, unified entity. Finding one would be as profound as discovering that electricity could exist without both positive and negative charges. It would complete a fundamental symmetry in nature, revealing a deeper elegance in the laws of physics. This glaring absence of monopoles is a classic puzzle in cosmology known as the monopole problem. If grand unified theories are correct, the seething energy of the early universe should have produced these particles in staggering abundance. There should be so many that they would dominate the mass of the cosmos, making our universe a very different place, and we should be tripping over them constantly. The fact that we have never seen a single one is a major contradiction. The most elegant solution to this mystery is the same cosmic event that gave us our smooth and flat universe, inflation. That brief period of hyper-fast expansion would have stretched the fabric of spacetime so dramatically that the density of any primordial monopoles would have been diluted to almost nothing. The few that might remain would be so incredibly far apart that finding one would be a monumental feat of luck. Imagine scattering a handful of sand across an entire continent. The chance of stumbling upon a single grain becomes infinitesimally small. This is why our most sensitive experiments have yet to find a monopole. Physicists have built vast detectors, some using loops of superconducting wire. If a monopole with the predicted immense magnetic charge were to pass through such a loop, it would induce a sudden, permanent electric current, a clear and unmistakable signature of its ghostly passage. Discovering a magnetic monopole would do more than just solve a cosmic puzzle. It would provide direct, experimental evidence for the grand unification of forces, offering a breathtaking glimpse into the universe's first moments when electromagnetism and the weak force were one. It would fundamentally rewrite our textbooks, proving that magnetism can exist in a pure, isolated form, a hidden potential within the fields that shape our reality. The true engine of that primordial explosion was a field unlike any other. The inflatoned field is the hypothesized cosmic agent responsible for the universe's breathtaking growth spurt. Think of it not as a force of push or pull, but as a form of potential energy, a kind of tension stored in the very fabric of space itself. In the universe's first fleeting fraction of a second, the inflatoned field found itself trapped in a state of false vacuum, a high-energy plateau that was unstable. This peculiar state of the field had a bizarre property. It generated a powerful, repulsive form of gravity. Instead of pulling things together, this repulsive gravity caused every region of space to push every other region away, triggering an exponential expansion that blew up a subatomic speck into a macroscopic cosmos in less than the blink of an eye. This was cosmic inflation, driven by the sheer energy density of this single, all-pervasive field, but such a state of affairs could not last forever. Like a ball perched on a hill, the inflatoned field was destined to roll down. Through a process called quantum tunneling, or simply a random fluctuation, the field eventually decayed. It fell from its high-energy false vacuum state into its true, lowest energy vacuum. The moment this transition occurred, the era of hyper-expansion ended. The immense potential energy that had been stored in the inflatoned field had to go somewhere. It did not simply vanish. In a colossal event known as reheating, that pent-up energy flooded the universe. The cold, empty expanse that had been stretched smooth by inflation was suddenly inundated with a seething, hot soup of particles. Every quark, every electron, Every photon that would eventually build our reality was created in this explosive release. The universe was instantly reheated to an unimaginable temperature, creating the hot, dense plasma of the traditional Big Bang. This is the profound link. The inflatoned field did not just create space, it filled it. Its decay was the trigger that set the entire subsequent history of the cosmos in motion. The quantum fluctuations in this field, stretched to cosmic scales, became the seeds for galaxies. The energy of its demise became the raw material for every star and planet. All the complexity and structure we see today was born from the death throes of this single, primordial field, the unseen catalyst that gave us both a stage and the players upon it. This same cosmic asymmetry between left and right extends into the heart of matter itself, creating bizarre currents where none should logically flow. The chiral magnetic effect is a quantum phenomenon that arises when a unique imbalance exists within a material. In the quantum world, many particles possess a property called chirality, which you can think of as a kind of handedness. A particle can be right-handed or left-handed, depending on the relationship between its direction of motion and its intrinsic spin. Under normal conditions, the universe seems to treat both hands equally. But in the presence of a powerful magnetic field and an imbalance between the number of left and right-handed particles, something extraordinary happens. An electric current spontaneously generates, flowing directly along the lines of the magnetic field. It is as if you could create a river of electricity simply by having more left-handed electrons than right-handed ones inside a magnet. This is not science fiction. It has been observed in sophisticated laboratory experiments with exotic materials, but its most profound implications are not on Earth. They lie in the most extreme environments the cosmos has to offer. In the first microseconds after the Big Bang, the entire universe was a seething soup of quarks and gluons, a state of matter known as the quark-gluon plasma. In this primordial furnace, immense magnetic fields, trillions of times stronger than any magnet on Earth, are thought to have briefly existed. Simultaneously, quantum processes could have created vast imbalances between left and right-handed quarks. These perfect conditions would have triggered a colossal chiral magnetic effect, generating massive currents that swirled through the infant cosmos. These currents could have amplified the magnetic fields further, creating a feedback loop that left a permanent imprint on the distribution of matter, potentially influencing how the very first protons and neutrons condensed from the plasma. This quantum anomaly did not vanish with the early universe. It may be actively shaping the most dense objects we know of today, neutron stars. These stellar corpses are essentially giant atomic nuclei, miles across, with densities so immense that a single teaspoon would weigh billions of tons. Their interiors are likely a soup of free-flipping quarks, and their surfaces possess magnetic fields of almost unimaginable strength. Here, the chiral magnetic effect could be continuously at work, driving powerful currents that contribute to the star's intense magnetic phenomena and perhaps even influencing the violent starquakes that ripple across their super-dense crusts. This reveals a universe where the abstract handiness of particles, combined with cosmic magnetic fields, can forge rivers of power in the void, orchestrating the behavior of matter from its first moments to its most exotic final forms. These primordial black holes would be cosmic fossils from the universe's first second. While the black holes we know form from the collapse of massive stars, these ancient entities could have been born from the raw density fluctuations of the Big Bang itself. In that searing, dense early universe, pockets of space could have become so overdense that they collapsed directly under their own gravity, bypassing the need for a stellar life cycle entirely. They could range in size from smaller than an atom to many times the mass of our Sun, all forged in the initial chaos. This leads to a fascinating possibility. What if these ancient black holes, drifting unseen through the galaxy for billions of years, are the very dark matter we have been searching for? They would exert a powerful gravitational pull, yet emit no light, perfectly matching the description of the invisible glue holding galaxies together. A universe filled with a vast population of such primordial objects could solve the dark matter puzzle in one bold stroke. Yet, if they are out there, how could we ever hope to find something so fundamentally dark? The answer may lie in their death. According to Stephen Hawking's revolutionary theory, black holes are not entirely black. Due to quantum effects at their event horizons, they slowly leak radiation and lose mass, a process known as Hawking radiation. For a massive stellar black hole, this evaporation is negligible, taking longer than the current age of the universe, but for a small, primordial black hole with the mass of an asteroid or less, the story is different. As they lose mass, they evaporate faster and faster, ending their lives in a final, explosive burst of high-energy radiation. We could, in principle, detect the gamma-ray flash of such an event. This would be a monumental discovery. Catching the death of a primordial black hole would be like opening a direct window into the first instance of the Big Bang, revealing the density of the universe at its birth. Even more profoundly, the precise nature of that final explosion would be dictated by the laws of quantum gravity, a theory that has eluded us for a century. By studying how these objects die, we could finally glimpse the hidden rules that unite the cosmos and the quantum, reading the final message of a relic from the dawn of time. The pressure of nothingness is real, and we can measure it in a laboratory. Place two perfectly smooth, uncharged metal plates mere nanometers apart in an absolute vacuum, shielded from every known force. Logic says nothing should happen, yet an invisible push forces the plates together. This is the Casimir effect, a direct and tangible pull from the quantum void itself. The cause lies in the restless sea of virtual particles that fill every inch of space. Outside the plates, in the open vacuum, virtual particles of all wavelengths can flicker in and out of existence. But in the narrow gap between the plates, only certain wavelengths can fit, much like how only specific musical notes can resonate inside an organ pipe. This restriction means that fewer virtual particles can pop into being between the plates than in the bustling void outside, with more activity pushing on the outer surfaces of the plates than on the inner surfaces. The net result is an irresistible force that drives them together. It is not a traditional attraction, but a push from the imbalance of the cosmos. This tiny, measurable force in a lab is our most direct evidence that empty space is not empty. It is a simmering cauldron of energy, a quantum pressure cooker whose fluctuations can literally move objects. The same underlying jitter that seeded the galaxies now nudges metal plates in a vacuum chamber, proving that the ghostly energy of the vacuum is not a mathematical abstraction, but a physical reality with tangible power. These ghostly particles are cosmic shape-shifters, rewriting their own identities as they race across the cosmos. Neutrinos are among the most abundant particles in the universe, yet they are famously aloof, passing through entire planets as if they were empty space. For decades, we believed they were completely massless, traveling at the speed of light without a whisper of resistance, but the universe had a surprise in store, a phenomenon so subtle it forced us to reconsider one of our most fundamental theories. This is the mystery of neutrino oscillations. A neutrino is born with a specific flavor, an identity tied to its interactions. It can be an electron neutrino, a muon neutrino, or a tau neutrino. But unlike a steadfast electron that remains an electron for all time, a neutrino does not stay true to its birth flavor. As it travels through the vacuum of space, it spontaneously transforms, morphing from one type into another in a continuous, silent dance. An electron neutrino produced in the heart of the Sun can become a muon neutrino by the time it reaches Earth. This metamorphosis is only possible if neutrinos possess mass, a tiny, but non-zero, amount of substance. The implications of this discovery were staggering. The standard model of particle physics, our most complete catalog of the fundamental building blocks of reality, had predicted for years that neutrinos were massless. Their oscillation and the mass it implies is direct evidence that the standard model is incomplete. There is physics beyond our current understanding, a hidden layer of reality where these particles acquire their tiny mass through mechanisms we have yet to uncover. This tiny mass has had a colossal impact on the evolution of the cosmos. In a supernova explosion, the collapse of a massive star's core releases an immense pulse of neutrinos, carrying away more than 99% of the star's final energy. The way these neutrinos oscillate as they flee the chaotic inferno, interacting with the dense matter of the dying star, helps drive the explosion itself. Their transformations can change the energy dynamics just enough to tip the scales, ensuring the star blows itself apart and scatters the heavy elements necessary for life across the galaxy. These shape-shifting phantoms are not just passive bystanders, they are active architects of cosmic death and rebirth, and their restless dance is a quiet, persistent clue to the deeper laws that govern our universe. The universe seems to know we are here. Its fundamental forces and constants are balanced on a razor's edge, a cosmic coincidence so precise it defies simple chance. The strength of gravity, the mass of the electron, the precise value of the strong nuclear force, each is set to a value that allows for the existence of stars, planets, and ultimately, life. If any one of these numbers were even slightly different, the consequences would be catastrophic. A fraction more strength in the strong force, and all the hydrogen in the early universe would have fused into helium, leaving no water or fuel for stars. A fraction less, and no stable elements beyond hydrogen could form. This apparent fine-tuning leads us directly to a profound and philosophical question, the anthropic principle. In its simplest form, it states that the universe must be compatible with the conscious life that observes it, because we are here to observe it. This is not an explanation, but a starting point for a fierce cosmic debate. One compelling resolution lies in the concept of a multiverse. Imagine our universe is just one bubble in an infinite, frothing sea of universes, each with its own random set of physical laws and constants. In the vast majority of these universes, the numbers are wrong. Stars never ignite, atoms never bond, and cosmic history is a brief, silent flash, but in an incredibly rare subset, like ours, the dice rolled just right. We should not be surprised to find ourselves in a universe that permits our existence, because in all the others, there is no one to be surprised. This view suggests there is no deeper reason for the fine-tuning, only a statistical inevitability given an infinite number of cosmic lotteries. The opposing perspective asks if this is a sufficient answer. Could the exquisitely specific laws that allow for consciousness be a hint of something more, a deeper layer of reality where life or mind is not a random accident but a fundamental feature of the cosmos? This is not necessarily a call for creator, but a question of whether the universe's capacity for self-awareness points toward an underlying principle we have yet to grasp. Are we simply the lucky winners of a cosmic dice game, or is our presence a quiet clue to the universe's true nature? The constants themselves hold the answer, but the key to reading them remains just beyond our reach. A quantum particle can exist in multiple places at once, a shimmering cloud of possibility, yet when we look at it, this ghostly superposition collapses into a single, definite location. The force responsible for this transition is not a conscious observer, but a relentless, invisible process called quantum decoherence. It is the mechanism that washes the quantum weirdness out of our everyday world, transforming a realm of probability into the solid, predictable reality we inhabit. Decoherence occurs because no quantum system is ever truly isolated. An electron in a superposition is constantly buffeted by a storm of interactions, exchanging tiny amounts of energy with the countless photons and other particles that fill even the purest vacuum. These interactions are like a constant, gentle measurement performed by the environment. Each collision records a tiny piece of information about the particle's state, effectively entangling the quantum system with its vast surroundings. This entanglement spreads the once coherent superposition across the entire environment, making it irretrievable for all practical purposes. The delicate quantum state loses its phase relationships, a process akin to a choir of singers all starting at different times, their harmonious wave collapsing into incoherent noise. The result is a world that appears classical. The moon is definitely in the sky, not in a fuzzy superposition of being here and there, because it is constantly interacting with sunlight, cosmic rays, and the gravitational tug of the Earth. Its quantum nature has been decohered by the entire universe. This process solves one of the great puzzles of quantum mechanics, explaining why we do not see quantum superpositions in our daily lives without needing a conscious observer to collapse the wave function. The environment is always watching, and its constant, chaotic measurement forces the quantum world to make a choice, solidifying probability into the single timeline we experience. Decoherence is the quiet sculptor of classical reality, carving the definite and the concrete from the raw, probabilistic marble of the quantum realm. The smooth, curved geometry of spacetime is written in a hidden mathematical language. This language is not built from words, but from a mathematical object called the metric tensor. Think of it as the universe's most detailed set of blueprints, a set of 10 numbers at every single point in space and time that defines the shape of reality itself. These 10 numbers are not arbitrary. They tell you everything about the local geometry, specifying how distances are measured and how time flows in that specific location. When a planet orbits a star, it is not following a command from a force, it is simply reading the local values of the metric tensor and tracing the most efficient path through that curved geometry. The subtle wobble in Mercury's orbit, a puzzle that Newtonian gravity could not fully solve, is a direct result of the Sun's mass minutely altering the values of the metric tensor in the space around it. The bending of starlight around a massive galaxy is not light being pulled, it is light traveling in a straight line through a space whose very definition of straight has been warped by the numbers in this cosmic blueprint. The metric tensor is the ultimate stage director for the cosmos. It does not dictate the script the actors will follow, but it defines the stage itself, its hills and valleys, its shortcuts and dead ends. Every particle, every ray of light, is an actor that must move according to the stage's hidden contours. This mathematical entity is why we say gravity is geometry. The force you feel is an illusion, a manifestation of you trying to move in a straight line through a universe whose stage is fundamentally curved. The metric tensor is that curvature, quantified and made real, the silent, invisible grid that gives gravity its form and power. Frozen into the fabric of the cosmos is a phantom echo, a sound wave from the universe's fiery infancy. These are Baryan acoustic oscillations, the fossilized imprint of a primordial roar that still dictates how galaxies are spaced today. To understand this, we must journey back to the universe's first few 100,000 years, when it was a dense, hot plasma of protons, electrons, and light. In this searing soup, gravity was constantly trying to pull matter together into denser clumps, but it had a powerful adversary, the intense pressure of radiation, which pushed back, creating a powerful outward force. This created a tug of war, a continuous cycle of collapse and rebound. A region of plasma would begin to collapse under gravity, but as it compressed, the radiation pressure inside would build until it was overwhelming, causing the region to explosively rebound outward. This created a spherical sound wave, a ripple of compressed matter and energy that propagated through the plasma at over half the speed of light. This cycle repeated across the cosmos, creating a universe filled with these expanding, overlapping bubbles of sound. Then the universe cooled. When it reached about 380,000 years old, a critical event occurred: recombination. Electrons combined with protons to form the first neutral hydrogen atoms. Suddenly, the universe became transparent. Light, which had been trapped, could now travel freely, and this is the light we see today as the cosmic microwave background. But for the plasma of matter, this was a sudden freeze. The sound waves, caught mid-propagation, were instantly locked in place. The ripples stopped moving, and the spherical shells of compressed matter were frozen into the distribution of the primordial hydrogen. These frozen shells became the preferred locations for galaxies to form billions of years later. Gravity pulled dark matter and ordinary matter into the denser regions, including these vast, fossilized spherical shells. This is why when we map the universe on the largest scales, we do not see a purely random distribution of galaxies. Instead, we find that galaxies are more likely to be separated by a specific, preferred distance about 500 million light-years apart. It is the signature of that ancient sound wave's maximum reach, a standard ruler etched across the heavens. This fossilized echo is one of the most powerful tools in modern cosmology. By measuring this preferred scale in galaxy surveys, astronomers can use it as a cosmic tape measure. They know the true physical size of this standard ruler from theory. By observing how large it appears to be at different distances, and thus different epochs in cosmic history, they can precisely measure how the expansion rate of the universe has changed over billions of years. This is exactly how astronomers confirmed the shocking acceleration of the cosmos, providing some of the most compelling, independent evidence for the existence of dark energy. The same oscillations that seeded the large-scale structure of the universe are now the tool we use to measure the mysterious force that is tearing that structure apart. These frozen cosmic strings are not the only possible scars from the universe's violent birth. When the fundamental fields cooled and settled into their current state, they may have trapped other, more complex imperfections within the fabric of reality itself. These are topological defects, not mere cracks, but intricate knots and boundaries that could not be smoothed away. A domain wall, for instance, would be a two-dimensional sheet, a vast membrane separating regions of space where a cosmic field settled into different states. Passing through such a wall would be like stepping from a universe where matter is subtly different into another, a border with immense density that could slice through galaxies. Even more bizarre are textures, which are not objects at all, but swirling knots of energy in the fields, dynamic and unstable twists in the vacuum that could unravel with tremendous power. These defects are like the grain in wood or the flaws in a crystal, permanent features imprinted during the freezing of the cosmic order. Their gravitational influence would be profound. A drifting domain wall could act as a titanic lens, warping the images of entire galaxy clusters behind it. The sudden collapse of a texture would release a storm of gravitational waves, ripples in spacetime that could be detected by our most sensitive observatories. Finding evidence of any topological defect would be like discovering the fossilized brushstrokes from the moment the universe's laws were set. They are relics from a time of ultimate change, and their existence would provide a direct, physical map of the abstract phase transitions that gave us the forces we know today, a hidden architecture written into the empty space between the stars. Our reality may be a projection, a cosmic illusion of breathtaking depth, The holographic principle is one of the most radical ideas in all of physics, a concept that rewrites our understanding of space, information, and reality itself. It proposes that all the information needed to describe everything within a three-dimensional volume, every star, every planet, every person, can be entirely encoded on its two-dimensional boundary. Think of a hologram, a flat, two-dimensional piece of film, when illuminated with a laser, projects a stunningly realistic three-dimensional image into the space above it. The principle suggests our universe might operate in a similar way. The three-dimensional world we experience, with all its richness and solidity, could be a grand projection from a vast, two-dimensional surface at the edge of the cosmos. This is not saying we are made of light, but that the information that defines us, the blueprint for every particle and force, is stored on a distant, lower-dimensional screen. The origin of this astonishing idea comes from an unexpected place, the study of black holes. Stephen Hawking discovered that when a black hole evaporates, it seems to destroy information, which violates a fundamental rule of quantum mechanics. Information, it is said, must be preserved. The holographic principle emerged as a brilliant solution. It states that all the information about what falls into a black hole is not lost inside its mysterious interior, but is instead perfectly encoded on its event horizon, the two-dimensional surface that marks the point of no return. The event horizon acts like that piece of holographic film, storing the data of everything that has ever crossed it. This logic was then extended to the entire universe. If it works for a black hole, could it work for the cosmos as a whole? The mathematics of string theory and quantum gravity suggest that yes, we might all be living inside a hologram, with the cosmic microwave background or some other faraway surface acting as the ultimate storage device. This reshapes our concept of dimensionality in a profound way. The third dimension, the space we move through, may not be fundamental. It could be an emergent property, a consequence of the vast amount of information processed on a distant, two-dimensional surface. The solidity of your hand, the vastness of a galaxy, the depth of space, all of it could be a magnificent projection, a cosmic sleight of hand where the true reality is written on a flat, infinite canvas at the edge of everything we know. This staggering mismatch is not a simple error. It is a screaming void in our understanding of reality. We calculate that empty space should possess an energy density of such immense power that it would have ripped apart every atom in the universe before they could even form. The number is so large it defies human comprehension, yet when we measure the actual energy of the vacuum, the force we call dark energy, it is almost zero. It is weaker than our prediction by a factor of 1 with 120 zeros after it. To put that in perspective, it is the difference between predicting that a single grain of sand should weigh as much as 1 billion galaxies and then measuring it to find it weighs, well, almost nothing. This is not a small discrepancy. It is the most spectacular failure of a theoretical prediction in the entire history of science, and it points directly to a fundamental flaw in our grasp of nothingness itself. The vacuum is not empty, but its true energy is a ghost we cannot yet catch. This catastrophe forces us to consider that the cosmological constant might not be a constant at all. What if dark energy is not a fixed property of space, but something that evolves? This idea leads to a dynamic field known as quintessence, a cosmic cousin to the inflaton field that drove the Big Bang. Unlike a static constant, quintessence is a field that can change over time, its energy density slowly rolling toward its minimum. This could explain why the vacuum energy is so small today, a temporary low point in a cosmic landscape that is still settling into its final form. It suggests that the acceleration of the universe might not be a permanent feature, but a phase that could eventually change, perhaps even reversing into a collapse. The cosmological constant problem is more than a puzzle, it is a profound question about the very ground state of existence. Why is the universe so close to nothing, yet just enough of something to allow for galaxies and life? The answer will require a revolution, a new principle that tells us why the chaotic frenzy of the quantum void ultimately adds up to such a profound and life-giving quiet. Perfection is a fleeting state, a moment of pure potential that cannot last. In the first searing moments after the Big Bang, the universe existed in a state of ultimate symmetry. The four fundamental forces we know today, gravity, the strong force, the weak force, and electromagnetism, were fused into a single, unified superforce. There was no distinction between them, no separate identities for particles. It was a featureless, hot, and perfectly balanced sea of energy, a blank canvas with no direction. But as the universe expanded and cooled, this perfect symmetry was destined to shatter. The cosmos underwent a series of cosmic phase transitions, akin to steam cooling and condensing into water, or water freezing into ice. With each drop in temperature, the underlying fields that govern reality settled into new, more stable states. During these transitions, the perfect symmetry was broken. Think of a perfectly round, smooth ball balanced on the very peak of a steep hill. This is the symmetrical state, but it is unstable. The slightest nudge, a random quantum fluctuation, will cause the ball to roll down into one of the many valleys surrounding the hill. The moment it chooses a valley, the perfect rotational symmetry of the hilltop is broken. The ball has picked a specific direction. The universe did the same thing. One of the most critical breaks occurred when the electroweak force split in two. In the extreme heat of the early cosmos, the electromagnetic force and the weak nuclear force were one and the same. The particles that carry these forces, the photon and the massive W and Z bosons, were indistinguishable, but as the temperature fell below a critical threshold, a cosmic field, much like the Higgs field, shifted into a new state. This breaking of electroweak symmetry gave the W and Z bosons their immense mass, while the photon remained massless. In that instant, the weak force and electromagnetism became two distinct phenomena with vastly different characters. One became the short-range force responsible for nuclear decay, the other the long-range force of light and chemistry. This single event determined the very rules of engagement for matter. The specific way the symmetries broke is the reason protons are stable, why stars can fuse hydrogen, and why complex atoms can exist. It locked in the masses of quarks and electrons, setting the values of the fundamental constants that allow for a rich and complex reality. Our universe is not a realm of perfect symmetry, but a world built from its elegant, creative, and necessary broken pieces. The quantum realm presents a final, unsettling possibility that the solid world you perceive is summoned into being by your own awareness. At the heart of this mystery lies the measurement problem, a deep puzzle about what actually happens when a quantum system is observed. An electron, until measured, exists in a blur of potential locations, a superposition of all possible states. The mathematics describes this as a wave function, a cloud of probability, but the moment a detector clicks or a human eye registers a result, that ethereal cloud collapses. The electron is suddenly, definitively in one place. The question that has haunted physicists for a century is simple: what triggers this collapse? One provocative, though highly speculative, interpretation suggests the trigger is consciousness itself. In this view, the physical apparatus of a detector is not enough. It, too, is made of atoms that can exist in superpositions. The final link in the chain, the thing that forces a single outcome from the sea of maybes, is the conscious observation of a mind. This idea frames consciousness not as a passive byproduct of brain chemistry, but as a fundamental force that participates in sculpting reality. It blurs the line between the observer and the observed, suggesting that the universe requires a witness to become concrete. This is not to say you can manifest a car by thinking about it. The probabilities are fixed by physical law, but your act of looking may be the final step that chooses one specific reality from the countless parallel possibilities the equations allow. The implications ripple out from the laboratory to the cosmos. If consciousness plays this role, then the universe we measure is not an independent, external construction. It is a collaborative creation, a dialogue between the physical world and the minds that perceive it. We are not just inhabitants of the cosmos, we may be its co-authors, our awareness the final ingredient that crystallizes the quantum potential into the tangible, classical world we share. This places our inner experience at the very center of the cosmic story, a profound and humbling reminder that the greatest unseen force shaping reality might be the one doing the looking. From the ghostly pull of dark matter to the repulsive push of dark energy, these 30 unseen architects have revealed a cosmos far stranger and more magnificent than we ever perceived. The quantum foam whispered the first seeds of galaxies, the Higgs field gave substance to a formless soup, and the strong nuclear force forged stable atomic hearts from chaos. We have journeyed through forces that connect particles across the universe, fields that stretched space itself, and a vacuum teeming with phantom energy. Each force, from the cosmic to the quantum, plays its part in an intricate cosmic symphony. They are not isolated phenomena, but interconnected threads in a single, magnificent tapestry, working in silent concert to weave the reality we are privileged to witness. This grand invisible machinery orchestrates everything, from the spin of an electron to the majestic dance of galaxy clusters, so the next time you look up at the night sky, remember that you are not just seeing points of light. You are gazing upon the visible signature of a hidden reality, a cosmos built and shaped by powers beyond our ordinary senses. We want to know which of these forces reshapes your understanding of the universe most profoundly. Share your thoughts in the comments below, and let's continue this journey of cosmic curiosity